goal of this project is to redesign an aircraft engine bracket with improved structural efficiency and sustainability. While the bracket itself doesn't operate under continuous dynamic loads, it plays a critical role in supporting the engine cooling during maintenance. Traditionally, this component is made from titanium alloy due to its high strength to weight ratio. However, titanium has an extremely high production energy cost, making it less sustainable in the long term. In this study, we have replaced titanium with magnesium alloy AZ80A-T5, a much lighter and more sustainable material, while ensuring the bracket can still meet all mechanical performance targets. Using CAD and CAE tools, we have applied structural, thermal, and vibrational analysis methods to confirm that the new design maintains safety, minimizes material use, and supports responsible manufacturing aligned with Sustainable Development Goals 12. This engine bracket is made from magnesium alloy AZ80A-T5, a lightweight material with good mechanical strength, making it suitable for load-bearing applications. From the linear static analysis in ANSYS, we observed that the maximum total deformation is 0.33499 mm occurring at the top mounting area, which indicates that the structure is sufficiently stiff. The equivalent von Mises stress reached a peak of 183.45 megapascals near the mounting face, which remains below the material's yield strength, confirming that the bracket will not experience permanent deformation under the given load. The minimum safety factor recorded is 1.88, which is above the typical design requirement of 1.5 for static loads, ensuring that the bracket is structurally safe. Overall, the analysis confirms that the bracket is reliable under static conditions, and areas with high safety margins present opportunities for material reduction to improve lightweight efficiency without compromising safety.
So, first of all, I will explain about the purpose of thermal stress analysis. There is a four main purpose for carry out this thermal stress analysis. The first one was to assess how the bracket behaves under temperature changes from 22 degrees Celsius to 200 degrees Celsius. And the second one is to identify stress concentrations caused by thermal expansion. And the third one is to evaluate deformation and safety factor changes. And the last one is to ensure the design remains safe and functional under operational heat conditions. And here I have included the comparison table for heat influence before and after in the model. So first of all, for the stress, without temperature change, it recorded under 83.45 megapascal. And with thermal change, it recorded 1156.8 megapascal. And for the total deformation, without thermal change, it recorded 0.33499 millimeter, and with thermal change, it recorded 0.62626 millimeter. And finally, for the factor of safety, without thermal change, it recorded 1.8806, and with thermal change, it recorded 0.29823. Next, there is three results that we gain from the NC software, which is equivalent von Mises stress, total deformation, and safety factor. And finally, now I will explain about the interpretation of result for the thermal stress analysis. So, the first interpretation is thermal expansion increases deformation. We can see that the deformation doubles from the initial value due to the temperature rises. So this is because the magnesium alloy expands when it is applied to a higher temperature, which causes it to increase in total deformation. And for the second is drop in mechanical strength at higher temperature. We can see that the stress increases drastically from under 83.45 megapascal to 1156.8 megapascal. This is because the magnesium alloy lose strength and temperature as temperature rises, leading to significant stress increases from under the same loading condition. And last but not least, the bracket is no longer safe at higher temperature. This is can seen by the reduction in the safety factor from 1.8806 to 0.29823.
The analysis had been conducted to identify the natural frequencies and mode shape of the bracket. 6 mode shapes had been observed, and each representing a different type of vibration such as bending, twisting, and local deformation. Mode 3 had shown the highest deformation for 14,047 mm, which indicated a critical vibration at the middle span of the bracket as shown in the table. All natural frequency had been higher than the engine excitation frequency, which is 275.8 Hz, with the lowest mode starting at 306.8 Hz. This has suggested that the bracket was very stiff and resonant, was unlikely to occur during normal engine operation. From the graph present, all modes had natural frequency far above 275.8 Hz, which is the engine excitation frequency. This confirmed that the bracket would not experience resonance during engine operation. The analysis had helped to understand the dynamic stability of the bracket, and this result could guide for future design improvement, especially at critical point like the middle span at mode 3 as shown in the table. In summary, Magnesium AZ80A-T5 had been selected for its accident lightweight and mechanical properties, making it suitable for aircraft engine bracket. The design passed the static analysis with safe deformation and factor of safety while maintaining a low weight of 0.619 kg. However, under thermal loading, the bracket experienced high stress, lowering the safety margin. Fortunately, vibration analysis showed all natural frequencies were well above engine excitation, confirming that resonance would not occur. Overall, the design was strong and stable under normal and dynamic conditions, but thermal resistance need to be improved.